Ever pop the tab on a cold drink and wonder exactly how it got into your hands? Perfectly filled, perfectly sealed, and perfectly packaged? Well, in today's Explainer, we're diving into the invisible, automated brain behind the modern beverage factory. We're going to look at exactly how engineers translate raw physical motion into the elegant mathematical language of PLC ladder logic. Just look at the incredible complexity of this setup. We're talking cans flying down conveyors at breakneck speeds, photoelectric sensors firing off, inkjet printers perfectly timing their spray, and robotic arms wrapping it all up. And the crazy part? This all happens continuously, reliably, and entirely without human intervention. So how do we actually turn all this physical chaos into perfect automated harmony? Because remember, machines don't have eyes and they definitely don't have brains. We get there by embarking on a massive translation journey. We literally have to take physical mechanics, the movement of aluminum and liquid, and translate them into abstract digital logic that a computer can rapidly process.
Here is our roadmap for this explainer. We'll start with 1, the physical factory line, then move to 2, the 5 golden rules, and 3, mapping senses and muscles. Then we'll really get into the weeds with 4, decoding the ladder logic, before wrapping up with 5, industrial hardware integration. Getting this vocabulary down is absolutely crucial before we dissect the actual code.
Okay, Section 1, the physical factory line. We're mapping the beverage can production line by starting with what we can actually see and touch right on the factory floor.
We're tracking a can as it travels from the filler machine on the far left, all the way over to the palletizer on the right. Notice how the can has to survive a literal gauntlet of specific stations. We've got prismatic reflectors bouncing light to photoelectric switches, conveyor belts, high-speed printers, wrappers. Every single millimeter of this line is meticulously designed for a very specific sequence of events.
Ultimately, the can travels sequentially through 3 crucial physical zones. Step 1 is presence and cap detection, where sensors verify a can is there and actually has a lid. Step 2 is inkjet printing, which triggers a high-speed printer at the exact millisecond the can passes by. And Step 3 is packaging preparation, where the system has to physically count the cans to group them into sets of 3 for the shrink wrapper.
Moving into Section 2, the 5 golden rules of control system operation. For these physical zones to function safely and efficiently, they have to obey some incredibly strict constraints.
These are the absolute laws that our upcoming computer code must strictly enforce. Rule 1, cap verification. We stop immediately if a cap is missing, nobody wants to spill. Rule 2, precision printing. Rule 3, batch counting in exact groups of 3. Rule 4, process interlocking, meaning if the packaging area jams, the conveyor has to halt. And Rule 5, a safety alert has to sound anytime that primary conveyor is stopped.
That brings us to Section 3, mapping senses and muscles in our automation architecture. Because before we look at the brain of this operation, we really need to understand its anatomy.
To program a machine, you have to start thinking like one. Think of input strictly as the machine's senses. This is what the machine uses to gather data from the outside world, like feeling a button being pushed or seeing a cap. Outputs, on the other hand, are the muscles. It's what the machine actually does to change the physical world, like firing up a conveyor motor or triggering an alarm. Check out how our specific system routes those senses and muscles. Up top, we have 7 distinct input senses feeding into our central controller. We've got start buttons, stop buttons, can detectors, inkjet triggers, you name it. The controller evaluates all 7 of those inputs and then commands 4 specific output muscles at the bottom, running the motor, activating the printer, sending a packaging pulse, or ringing the safety buzzer.
All right, Section 4, decoding the ladder logic. We're translating the factory floor into code, finally dissecting the brain that connects those senses to those muscles. Here is the complete ladder logic diagram. If you haven't worked with one recently, just picture a literal ladder. The vertical rails act like pressurized water pipes, and the horizontal rungs are like valves. Power flows left to right, and execution flows from top to bottom. Because we really want to teach this carefully, we aren't going to rush. We're going to dissect this logic zone by zone.
Starting at the top, Zone 1 is our main drive and safety alarms. Look at that very first rung. You've got IN1, the conveyor start button. Press it, power flows across, and it flexes the CR1 output muscle to run the conveyor. But check out the parallel branch right underneath IN1. That's a classic latching circuit. It creates its own path for power, meaning the conveyor keeps running even after you let go of the button. It stays latched until you hit IN2, the stop button. And right below that, That's the alarm logic. If the conveyor's off, it explicitly commands the CR4 alarm buzzer to turn on.
Moving down to Zone 2, we get to the cap detection fault logic. This is beautifully designed. You've got input IN3 checking if a can is there. Right next to it is IN4 checking for the cap. See the line through IN4? That means it's a normally closed contact. It's basically asking the system, is the cap not there? So, if a can is present, but the cap is not, power flows straight to timer T1. That timer waits for a set delay, then smartly sends a signal right back up to Zone 1 to break our latch and safely halt the whole system.
Next up is Zone 3, handling the precision inkjet timing logic. When input IN5 detects a can in the exact right spot, it triggers output CR2 to fire the inkjet muscle. But obviously, you need incredibly precise timing for a moving target. That's where timer T2 comes in, set to a constant of 2. It guarantees the inkjet applies ink for the absolute perfect duration before shutting off and resetting for the next can.
Finally, Zone 4 at the very bottom handles the palletizer action using counting logic. Every single time a can passes the sensor, input IN6 pulses. That pulse feeds straight into counter C1. It literally clicks up 1, 2, 3. We've programmed a constant of 3 in there, so the second it hits that number, it triggers output CR3. That sends a pulse to the packaging machine saying, hey, batch is ready, wrap it up. Then it seamlessly resets to 0 and starts over.
Let's bring this all together with a diagnostic matrix that flawlessly maps the physical scenarios to our code. Let's trace the missing cap scenario we just talked about. The physical input condition sees the can, so that's a 1, but doesn't see a cap, so that's a 0. The logic action activates timer T1, which breaks our main latch. And the active output? The CR4 alarm turns on and the CR1 conveyor turns off. The logic absolutely nailed the golden rules.
Now Section 5, Industrial Hardware Integration. Because making it real means taking all this beautiful software logic and putting it to work in a harsh, physical factory environment. This visual perfectly bridges the gap. The abstract, digital ladder logic on the left gets systematically loaded into the rugged hardware controller on the right, like this Siemens S7 series PLC. This is where the physical wires from our real-world sensors actually terminate, and where the heavy, high-voltage motor relays begin. It's evaluating our digital ladder logic millions of times a minute to drive instant physical action on the floor.
We've gone from the chaotic movement of cans, established strict operational rules, mapped our senses and muscles, and decoded the elegant architecture of ladder logic. I really hope this explainer changes how you look at the automated world. Because the next time you pop the tab on a perfectly capped beverage, will you just see a drink, or will you see the invisible logic running the machine? Keep learning, keep analyzing, and we'll catch you in the next explainer.